Now let's talk about quantum numbers of these elementary particles. And as we know that these quantum numbers, what they do is they describe values of concerned, the values of the conserved quantities in quantum system. And they are relevant only in the regime of microscopic world. And these and their relevance in this microscopic world or microscopic system only. In case of microscopic particles, what we have is the quantum numbers are these quantum numbers are defined as the set of some numerical values. They are the numerical values which basically give the give solution of Schrodinger's wave equation. Schrodinger's wave equation. And when we have the solution of the Schrodinger's wave equation on applying this wave equation to the hydrogen atom, we come up with some numerical values, and these numerical values describe the quantum numbers of atoms. So quantum numbers basically describe the what they describe is the energy levels of electron in the hydrogen atom. If you have hydrogen atom, so these set of quantum numbers that we have, they give us they basically describe the energy levels of these electrons in atoms. And the laws of conservation of physical quantities, like we have conservation of energy, and we have conservation of angular momentum, linear momentum, and conservation of charge. I mean, they hold good in classical as well as in quantum mechanics. Now, in addition to these laws of conservation, in elementary particles have certain properties, and these properties are called as quantum numbers, which are also conserved, and they are conserved in a given reaction or a decay process. So let's try to analyze. Let's start with spin. Let's discuss some quantum numbers that are linked with these elementary particles. Now, the very first thing is spin, S. Now, every elementary particle spins. It has spin like the spinning of Earth on its own axis. And spin is the property of these elementary particles, which distinguish this elementary particle from other elementary particles. Now, I can say, in other words, that elementary particles are classified into two categories, depending on the value of this spin possessed by this elementary particle. Now, say for example, talking about bosons. And these bosons, they are elementary particles, and they have a spin. They have a spin of integral multiples. Spin of integral multiples. Multiples of h bar. Whereas talking about fermions, as elementary particles, they have half integer multiple of h bar. So I can say here that there are 2s plus 1 components of spin along the third axis. And they are denoted by, say, S3, and this S3 is, it is 2s plus 1. Now, for electron, if I choose an electron, what is S? S is half. So this S3 What will be S3 in this case? That will be S3 is 2 times 1 by 2 plus 1. So 2 and 2 will go, 1 plus 1 will give me 2. So this S3 comes out to be 2. So what does it mean? It means that the possible values for this S3 are, in case of electrons, they are plus half, which we can call as up spin, spin up, and minus half, this is spin down, or call it down spin. So what S3 gives us here is plus half and minus half. Now talking about the total angular momentum. Total angular momentum. What is the symbol? That's J. Okay. So this J is a vector, and the total angular momentum of the system of particles is basically the vector sum of the orbital angular momentum. So L is an orbital angular momentum, and the intrinsic angular and intrinsic spin angular momentum. So what we have is J is L plus S. So this J is under root of J times J plus 1 H bar, and this S is under root of S times S plus 1 H bar. And this L that we have is under root of L into L plus 1 H bar. Now, the total angular momentum has two discrete values here. What is that? One is L minus 1 and another is L plus 1. So for L equal to 1 and S equal to 1 by 2, what will be J? J will be 1 by 2 when you subtract them, and J is going to be 3 by 2 when you add them. So the values of the third component, which I'll choose it here as J3, they are going to be 2J plus 1. So what will be this 2J plus 1? So what I have here is J3 is 2J plus 1. Now for J equal to 3 by 2, what will be J3 in that case? That will be 2 times 3 by 2 plus 1. And this 2 and 2 will go, so for this I'll have 4 values. Hence we will have 4 values here. So what will be there? The 1 will be minus 3 by 2. It will be minus 1 by 2, plus 1 by 2, and plus 3 by 2. Now, talking about the charge Q of these elementary particles can have positive charge, they can have negative charge, or they can't have any charge. They will have zero charge, they will have neutral charge. And they are generally written as their charge is written in terms of plus E and minus E and simply 0. And this E is the charge of an electron, 1.6 times 10 to the power of minus 19 coulombs. If I choose the electron, so it is minus E, so it will be minus 1.6 times 10 to the power of minus 19 coulombs. Now, the electric charge associated with the with proton is plus E. The electric charge that's associated with this electron is minus E. And the electric charge that's associated with the neutron is 0.